All right, before I progress on to van der Waal interactions, let me add a few points about hydrogen bonds. Um, so hydrogen bonds are kind of a part of a whole spectrum of what we call electrostatic interactions. And in reality, all these weak interactions are based in some sort of electrostatic interaction, meaning that there's some type of positive and some type of negative charge associated. Here we have these polar bonded molecules that have these partial charges inherently there. Also keep in mind that you can have interactions between something that is partially positive and a negatively charged full ion instead of having just a partial negative ion. So you could have something like a chloride ion, which has a full negative charge, that could interact with the partial positive charge of the hydrogen on water. Okay, and this is actually what leads to salt dissolving in water, is the fact that you have these partial positives and partial negatives interacting with actual fully charged ions. So you can actually have a whole spectrum of these type of interactions between things that are polar, things that are already charged. You can have interactions between things that are partially charged and things that aren't charged on their own but can be induced to be charged under the right conditions. So there's actually a whole spectrum here. What is special about a hydrogen bond is most other positive-negative electrostatic interactions are very much dependent on the distance between the two ions, or the two partial charges. So the closer they are together, the stronger the attraction is. And I'm sure you've all seen this with magnets. You've probably played the game where you get two magnets as close together as you possibly can, and you nudge it a little bit forward, then all of a sudden, click, they come together. Okay? We've probably all done that. So the power of those electrostatic charges tend to get stronger the closer you get together. What's unique about hydrogen bonds is the distance between these atom centers. So the nucleus of this hydrogen and the nucleus of this nitrogen, in this case, is actually a fixed distance. And the only other place you see that is in covalent bonds. So the distance between this oxygen and this hydrogen is a fixed distance. Whenever you have water bonded to hydrogen, you always get this same distance. So hydrogen bonds seem to have some properties that are almost covalent in nature. And hydrogen bonds tend to be slightly stronger than you would expect them to be otherwise. So hydrogen bonds are kind of special category. Now, van der Waal interactions are another special category. And van der Waal interactions can be somewhat difficult to understand, so you might have to watch this a few times to get a handle on it. Okay? Van der Waal interactions happen on molecules that have nonpolar bonds. Okay? And in this scenario, these two nonpolar entities, here I have two hydrocarbon chains. So these are two kind of oily substances that are out there, made up of solely carbon and hydrogen. Okay, these are all nonpolar bonds. So carbon-carbon bonds are nonpolar, carbon-hydrogen bonds are nonpolar. There's nothing partial charged about it in any way, shape, or form. Now, if you take these two molecules and force them together artificially through some other type of force, you can cause something unique to happen. So I have a little animation that I'm going to start here. So when you have electrons that are being shared by these nonpolar bonds, they are being shared equally. So part of the time they're going to be in between the molecules, other part of the times they are going to be solely around the hydrogen, other times they're going to be closer to the carbon, but they're always moving. Okay? The same is going to be true for this top molecule, but I've kind of put this top molecule in freeze frame for a second, just to make it clear. Now, what I'm going to do is I'm going to start pushing these together, and something interesting is going to happen. The arrangement of charges on one molecule is going to start affecting the charges on the other molecule. Okay? Now, as these get pushed close together, where these electrons happen to line up appropriately, so you have this electron being kind of on the outside of the hydrogen, its partner across the way, its electron is more towards the carbon. Okay? Which means that for that one brief, ever so brief moment in time, that hydrogen does have a partially positive charge. But it's only temporary. It's only there for a brief fleeting moment. When you push these molecules close enough together, those brief fleeting moments where you get a partial negative and a partial positive lining up at the exact same position, which it's really only a matter of time before that occurs all along this molecule, you start to get bonds forming. Okay? And this actually stabilizes the location of those electrons. So this electron here will tend to stay on the outside of that hydrogen in proximity to this other hydrogen. And the electron that is up here will tend to stay slightly closer to that carbon. That in turn is actually going to impact the electron that is being shared, the electrons that are being shared between this carbon and this hydrogen as well. So it kind of has a chain reaction. As you start to build these, you get these minor partial induced, partial positive, negative interactions. Okay? So the question then becomes, okay, you get all these little minor bonds forming, they become stabilized. If you get enough of those, they can actually form a fairly strong interaction. Okay? Strong enough that this is actually how geckos climb up glass walls. Okay? They have these little hairs on their feet that are coated with nonpolar particles, and as they start touching the glass surface, they push their hands into the wall, and those hairs become in close contact with the glass material, which has various electrical charges already associated with it, and the nonpolar interactions on those hairs start to stabilize and form this Velcro-like connection. Okay? This can also happen when you take fatty material and push it closer together. Well, how would you push fatty material close together? Well, actually, if you put fat in water, the water tends to push the fat out. And we'll go into more detail about this later, and we'll come back to this. But whenever you have some type of artificial force pushing these nonpolar molecules together, you can induce a temporary polarish interaction. And this is something that we call van der Waal interactions. So it's something that takes some work to get to, but it's powerful enough that a gecko can walk up a glass surface. Okay? And it becomes an exceedingly important interaction when we start talking about how proteins fold and how they end up becoming something functional. Okay? So, as a recap for concept 2.3, the formation and function of molecules depend on chemical bonding between atoms. Things we discussed is the idea of in order to get a full outer valence shell, these atoms can share electrons. Those shared electrons form something that we call covalent bonds. You can have single covalent bonds, you can have double covalent bonds, you can actually have triple covalent bonds. And when you have covalent bonds, those two atoms will stick together and become something called a molecule. And that molecule acts as a single entity. Depending on what atoms you're talking about, you can have various different levels of interaction. So here we have carbon combined 4 things. Here oxygen combined 2 things. Here, instead of oxygen binding 2 things, it just forms a double bond with itself. Okay, so you can see all these variations. If this covalent bond forms on an electronegative element, and for us that is primarily talking about oxygens and nitrogens, you can produce a molecule that has partial positive and negative charges associated with it. Okay, we also have ionic charges where you have only one to give up or only one to gain, and it's much easier just to get rid of that electron, give it to something else, and then your next shell down is in fact fuller. This, of course, produces both cations and anions, positive ions and negative ions. Also changes the size of these atoms. And as a result, they tend to stick together and form things such as crystals. You also, in addition to these stronger bonds, such as covalent and ionic bonds, we have weaker bonds, such as hydrogen bonds, a whole slew of electrostatic interactions, and ultimately van der Waals interactions, which itself is kind of a forced electrostatic interaction. All right, so that is concept 2.3.